So when we talk about arenes, right, the simplest arene, as I mentioned before, is benzene. Okay, and benzene ka jo structure hai, it's like this. It's a hexagon. It's a circle inside a hexagon, and we'll just look at what the circle represents. Now, when we have this structure, right, इसका जो molecular formula होता है benzene का, molecular formula of benzene is C6H6. So what does that tell you about the carbon atom? How many atoms is each carbon atom bonded to over here in total? How many atoms is each carbon atom bonded to in total? Total में एक carbon atom अगर आप देखो, ये carbon atom let's say, how many atoms would this be bonded to? एक carbon, दो carbon और तीसरा फिर क्या होगा? एक क्या होगा यहाँ पर? Hydrogen होगा ना? So each carbon atom is bonded to 3 atoms. So in benzene, each of the carbon atoms is bonded to three atoms. Okay, it's bonded. Each carbon atom is bonded to 2 carbon atoms, and it's bonded to a hydrogen atom. Now, one thing that we observed about benzene is, so then what does that tell you? Is it a saturated compound or an unsaturated compound? Each carbon atom is not making 4 bonds, it's only making 3 bonds. So what does that tell you? Is it a saturated compound or an unsaturated compound? It's an unsaturated compound, right? अगर saturated होता तो हर carbon 4 atoms से bonded होता, but that's not the case. So then what are we left with? Then if you think about it, what we have is, right, there was a guy named, I don't know how to pronounce his name, Kekule. I think this is how he pronounced his name. Okay. And he said, you know what, benzene का molecular formula C6H6 है. तो what I believe is कि benzene का structure ऐसा होगा. उसने ये structure propose किया. आपको American textbooks में ये structure मिलेगा बना हुआ. Okay. He proposed this structure of benzene. Okay. And he said, you know what? We're alternating between double bonds and single bonds. So each carbon atom is making a double bond and a single bond, and it's bonded to one hydrogen, right? So I'm just going to show the hydrogens here. I haven't shown them on the left, but I'll show them here. So he proposed the structure of benzene. He proposed the structure of benzene as C6H6. But there was one problem in the structure. My question to you is that, what do you think, which bond do you think is shorter? Do you think a double bond is shorter or a single bond? Do you think a double bond is shorter or a single bond? A double bond is shorter, right? A double bond is shorter, not stronger. Between two identical atoms, a single bond would be longer than a double bond, because double bond में क्या होता है? You have stronger electrostatic forces of attraction, so the atoms are held closer together. Yeah. But what we observed about benzene, was that all the bonds were of the same length. So if all the bonds are of the same length, then do you think this structure is a correct structure? Or does this structure accurately represent what's happening over here? So it doesn't, obviously. So the answer is no. Because, as I said, if you look at this structure, okay, based on this structure, okay, this guy said that, you know what, iske benzene mein alternating single and double bonds hote hain. That would give it the formula C6H6. However, हमारी observation, structure की observations से हमें पता चला कि सारी bond length same है. अब अगर double और single bonds alternate कर रहे होते तो bond length same होती सारी. Wouldn't the double bonds have been shorter than the single bonds? Right? If we had actually observed it, if we hadn't observed it, if we didn't know, we would have based on this structure alone, we can say that the bond lengths would be different. But based on our observations, we observed that all the carbon-carbon bonds are of equal strength. Okay, they have the same bond strength or bond energy, and they have the same bond length. So that doesn't apply, because again, double bonds would be stronger and shorter. But the reality is that all the bonds are identical in benzene. So then this structure, even though it is used quite extensively, is not the most accurate representation of benzene. So we use this representation. Now what does this representation mean? Well, let's think of it this way. Okay. Let's look at each carbon atom in benzene. Okay. So let's say that we start with carbon, carbon. So let's just look at two carbon atoms here first, right? Now each carbon atom is making 3 bonds, right? It's bonded to 2 carbons and it's bonded to a hydrogen. So if it's making a total of 3 bonds, what do you think the hybridization of each carbon atom is? What's the hybridization of each carbon atom? So what we have is we can clearly see that if each carbon is bonded to 3 atoms, if each carbon is bonded to 3 atoms, this is sp2 hybridized, right? It's making 3 sigma bonds. But then, how many electrons does carbon have in its outer shell? How many electrons does carbon have in its outer shell? It has 4 electrons. So now we can see over here clearly that this carbon is sp2 hybridized, and how many of its 4 electrons are actually participating in bonding, in sigma bonding? Only 3 of them. So can I say that the fourth electron is in an unhybridized p orbital? Because 3 में से 2 p orbitals तो hybridize हो गए, लेकिन जो तीसरा p orbital है उसमें we have an electron, right? And that p orbital isn't hybridized. Agreed? Can I say the same thing for this carbon? Right? One of the electrons is not, and this electron is obviously can be found above or below the carbon atom, right? So then this is the kind of structure that we get over here is this, okay? So I'm just going to show you a diagram that shows the structure. So this is what the diagram for benzene looks like right here, okay? Now if you look at this quite clearly, what do you see here? What we see is that, you know what? We can clearly see that each of the carbon atoms is bonded to 3 other atoms, right? So it's sp2 hybridized, okay? And what we also clearly see is that we have p orbitals, and each of these p orbitals has an electron, right? And these electrons, we have 6 carbon atoms, okay? We have 6 carbon atoms, and so therefore we have how many? We have 6 pi orbitals, or p orbitals, sorry. Okay, so we have 6 p orbitals over here. Okay, and each of them has an electron, and what happens is that instead of let's say 2 carbon atoms here forming a pi bond, and then 2 carbon atoms here forming a pi bond, and then 2 carbon atoms here forming a pi bond, what happens is that they all sort of form this giant 6 carbon pi bond. So the 6 p orbitals overlap to form one giant pi bond. Okay, that's what this ring represents. Normally pi bond हम लोग किस तरह से represent करते हैं? It's between 2 atoms, right? So like carbon carbon यहाँ, carbon carbon यहाँ, carbon carbon यहाँ. But in benzene, what happens is that the p orbitals of all the 6 carbon atoms overlap, okay, together to form this giant sort of, you can think of this like a giant pi orbital. Okay, it's not really a pi orbital, it's like a delocalized ring of electrons, but all 6 of these p electrons are delocalized into one giant pi bond, so to speak. Okay, so this is where the ring in the structure of benzene comes from. And the reason why, rather than taking this structure, this kind of a configuration makes benzene a lot more stable. And we'll just talk about why it makes it more stable. But this is why we get the structure of benzene the way it's written. Now this phenomenon over here where you have delocalization of electrons, right? Now what's happening is that instead of the electrons being localized, instead of forming regular pi bonds in which, you know, you'd have 2 carbon atoms के p orbitals overlapping like this, what happens is कि सारे 6 के 6 carbon atoms के p orbitals overlap एक साथ. Okay, they overlap एक साथ, which means that the electrons are no longer localized between just 2 carbon atoms. The electrons are delocalized over all 6 carbon atoms. So you have this giant, the delocalization basically means now they're occupying, the electrons are free to move anywhere over the entire molecule, right? In the p orbitals, or in the delocalized sort of electrons in the p orbitals, right? So what we have over here is this phenomenon over here is known as resonance. Okay, this term of resonance is not part of your syllabus, but we'll still write it down to explain why this happens. Now, why is it more stable to have a structure like this as opposed to having a structure like this? Why is this more stable? Why is it better, or why is it more stable for the electrons to be delocalized over the entire ring, than to form localized pi bonds? Any suggestions? So here what you have is, because the electrons are essentially occupying a larger space, right? They're occupying a greater volume. Because the electrons are occupying a greater volume, right? There's a decrease in repulsion and therefore an increase in stability. Okay, so that's why resonance, or the overlap of all the p orbitals, is preferred. Delocalization of electrons is preferred to localized electrons. So rather than having localized electrons within these pi bonds, it's more favorable energetically for all of these p orbitals to overlap to form this one giant sort of pi bond. Okay, so these are called the delocalized electrons of benzene. And benzene is said to be the, and जो आपके जो aromatic compounds होते हैं, okay, benzene is said to be the simplest aromatic compound. Benzene is said to be the simplest aromatic compound. Okay, and in aromatic compounds, this is what you see. In all aromatic compounds, what you're always going to see is delocalization of electrons. You'll always see resonance. Resonance is basically when these electrons are delocalized over a larger space rather than just between two atoms. Okay, and aromatic compounds are much more stable as a consequence of resonance, or as a consequence of delocalization of electrons. Okay, so now let's look at the structure of benzene. Okay, or let's write down in detail how we can describe the structure of benzene. So first of all, what you have is, okay, so we're going to describe the structure of benzene. Okay, I'm going to draw the ring over here. Okay, so now if you look at the structure of benzene, now we've already seen that the carbon atoms are sp2 hybridized. So what do you think the bond angles are in benzene? The carbon-carbon bond angles. This bond angle. All the bond angles are what? Any idea? In benzene, if it's sp2 hybridization, what are the bond angles in benzene? So all the bond angles are 120 degrees. Okay, in the molecule, right? So it has bond angles of 120 degrees. Okay, and what we've already seen is that because of this delocalization of electrons, what you have is that all the bond lengths are the same and all the bonds are equally as strong. Okay, so we can say, when we talk about the structure of benzene, we can say that we call it a 6 center delocalized. We call it a 6 center delocalized pi bond, right? 6 center means that the pi bond, or the pi bond essentially extends over 6 carbon atoms. So you have 6 p orbitals overlapping to form a giant sort of pi bond. Okay, and the 6 center delocalized pi bond results in the following. Okay, thing. Now what we have over here is that, first of all, we can say, okay, that when we talk about benzene, right, we can say that all the carbon atoms are sp2 hybridized, right? And because you have this pi bond, what that results in is the fact that all the carbon-carbon bond lengths are equal. Okay, and since we have sp2 hybridization, what do you think that makes benzene? Do you think benzene is a planar molecule or a non-planar molecule? Do you think benzene is a planar molecule or a non-planar molecule? It's a planar molecule, right? It's a flat molecule because it's sp2 hybridized. So what you have is, okay, you have all carbon-carbon bond lengths are equal, right? We can say that all the bond angles are 120 degrees. So then what type of a shape is benzene, do you think? You have a planar molecule that's 6 carbon atoms. And all the bond angles are 120 degrees. What kind of a shape is that? You have a flat shape with 6 sides. What kind of a shape is that? You have a flat shape with 6 sides. What's the shape called? That's a hexagon, right? So benzene is actually a regular hexagon. Okay. Resulting. So this results in a planar, okay, regular hexagon shape. It's a regular hexagon. Regular hexagonal shape. Okay. Another thing that this delocalization does is that unlike alkenes, just when the double bonds were much more reactive, the pi bond was very reactive in alkenes. Does anyone remember the reaction that alkenes underwent? It was called what? What's the mechanism that alkenes? No, the mechanism, not the reagent. The mechanism is called for alkenes. Here, because of the delocalization of the electrons, right? Delocalization की वजह से क्या होता है? What happens is that it results in benzene being much more stable than alkenes, even though it's unsaturated, just like alkenes. Okay, benzene, due to delocalization, benzene is a lot less reactive, okay, than alkenes. Okay, hence it does not undergo electrophilic addition reactions. The reason why it's said to be a lot less reactive is because delocalization of electrons, right, increases the stability of the molecule. So because of stability, right, it when something is stable, it means that it doesn't react as easily. And obviously, as a consequence, we can clearly see that. So this pi bond, okay, this delocalized pi bond makes benzene a lot more stable. So in an exam, okay, and this question I think has shown up for 5 marks before. Okay. In an exam, right, if this question does show up, what you have to say is a question has shown up, okay, describe the structure of benzene. Okay. So what you would say is that, well, first of all the carbons are sp2 hybridized. Okay. And because the pi electrons in benzene are delocalized, it makes all the carbon-carbon bond lengths equal in length. Okay. All the bond angles are 120 degrees, which results in a planar hexagonal shape. Okay. Also, because of delocalization making the molecule more stable, we know that benzene is a lot less reactive than alkenes because it doesn't undergo electrophilic addition. Okay. And we can also say at the end of the day, okay, because of delocalization, we can also say over here that right, all the carbon-carbon bonds, right, are equally as strong. Right? That's not really a commentary on a structure, but rather on the fact that because they're identical bonds, right, they're also all equally as strong. So this is really the description of benzene and its structure and properties. Okay. And obviously we can see over here that we can also say that this pi bond makes benzene a lot more stable than expected.